Yeah, so today we're going to talk about empowering security with generative AI. And this is a topic that the more I read about it, the more experiments I run, it starts to make more sense that it's actually helping us to do our jobs, in my opinion, a little bit faster. It's actually enabling a lot of new capabilities that, in my opinion, are going to be super helpful for a lot of security researchers on the offensive and defensive side of the house. And my voice sounds a little different thanks to the ship yesterday and the beer. Actually, I like this voice right now. So this is going to be just sharing my journey to understand some of these concepts. I'm not a mathematician. I'm not a data scientist. I'm just a security researcher trying to share some of my notes, some of my experiments, and hopefully this makes sense. And you can also leave this presentation with some new knowledge about how to use AI in your job. And once again, I'm an AI cybersecurity enthusiast. So maybe after this talk, you can put that in your LinkedIn, in your Twitter, whatever you want. And of course, this is just my work. Most of it is usually outside of work currently because so I'm helping some teams internally, but this is a lot of the stuff that I've been trying just to do on my own. A couple of weekends, just trying to read, install a few things, and just share it with the community, right? That's the goal. And I'm a security researcher for the Microsoft Security Research Organization. And this is my beautiful dog, Stevie. And this is one of the perks of working from home. I love it. She still thinks she's a puppy, so she lays on my lap. She's a Great Dane, 125 pounds. That's a lot. I'm also the founder of the Open Threat Research Community. And I love dogs and open source in that specific order. And if you want to learn more about my open source contributions, you can go to the OTRF GitHub repository. So today we're going to talk about some of the fundamentals, how to get to a GPT model, at least, like how to actually understand these large language models. And then we're going to go through some of the basics of what GPT models are, and then also show some demos. Hopefully we can spend most of the time on the demos, but it is very important to understand the fundamentals, because even to understand the name GPT, you need to understand at least 2 to 3 concepts before you get there. And that's the goal for today, right? So the fundamentals, once again, this is the only potential mathematic just formulas you will see just in an image. And this was generated by Midjourney. So all my pictures do have the prompt at the bottom left. So if you want to generate something similar, you can just use that. So let's start with the basics. What's AI, right? What's artificial intelligence? And artificial intelligence is just a way to use algorithms that would enable machines to mimic human behavior. And at the same time, this human intelligence is actually the ability to be able to process information and be able to use that information to then make a prediction or perform a task. The AI models actually would learn from the data, right? Sometimes it would actually do it on its own. Sometimes it would need actually someone to tell it how to learn about the data, right? But that's just the basics of what AI is. AI is not new. It's been around since 1940s, 1950s. Actually, the term AI was coined, artificial intelligence, was actually coined in a conference in New Hampshire. I like to do history before we talk about the concepts, because this is very important. Then machine learning is a subset actually of AI, right? So now we start kind of understanding like, wait, what's the difference between AI and machine learning, deep learning? It's a subset of AI, right? And the idea here is how we move from taking a model to do a couple of tasks based on some conditions to now say, hey, I want you to learn from data now. This is the data. These are some examples. Now I want you to perform some of the tasks yourself. And the next concept is deep learning. Deep learning is a technique of machine learning. Once again, these are just my notes, okay? So we're not gonna get into like some of the mathematics things in here, but just to kind of show you exactly where they fit. Now, deep learning takes the concept of learning a little bit to the next level, in my opinion. It uses the concept of neural networks and actual deep neural networks. We're gonna talk about that in a little bit. But the idea here is that it could actually have these large models that would allow to learn, for example, from massive amount of data. And most of this learning, it does it on its own, for example. And it's going to make sense in a little bit. In this area, Transformers in 2017 is one of the discoveries proposals of a new way to translate text, for example, using neural networks. And this Transformers is the foundation of a lot of these large models that exist today that have been released in the past 5 years. And there is where we are currently, where we're talking about this concept of generative AI. We have been exposed to generative AI in 2022, for example, through a chat, right, bot. And now we're kind of just generating so much content using a model. That's generative AI. And in these concepts is where this use of these models becomes a foundation model, which means that now we are dealing with models that are capable to perform different tasks with foundational knowledge. Understanding language allows it now to, for example, write a letter for you, write a poem, predict, for example, the next word for you. It's going to answer questions. It's because it has so much knowledge that has been trained with that now we can actually, right, perform a couple of tasks for you. And some of those are generating content, right? So we are in this area right now. So let's start from the basics. What's a neural network? Okay, hopefully this will make sense. So a neuron, it's known as the perceptron. Perceptron has an input and output. Input is the features of data, let's say attributes of something that you want to use for the neuron to predict. The output is the prediction, right? In order to go from input to output, there are going to be these concepts of weights, numerical values that will transform the input and then will actually make it to the output. And there is the concept of activation functions, which acts as our neurons in our heads. Some neurons are enabled, some neurons are not enabled, activated, not activated. These activation functions allows us to take the input and put it into a scope of, let's say, 0 to 1 to provide some type of output. You can have a neuron, you can stack the neurons, you can have multiple layers of neurons, and those are known as the hidden layers in a neural network. You have an input and you have an output layer, as I mentioned before. If you go from left to right, that's known as forward propagation. And the reason why I'm talking about this terminology is because when you start reading papers, when you start reading some of the architectures of transformers, you're going to start reading about that, like feed-forward neural networks. Well, this is what it is. Like when you go from left to right, input to output, forward propagation. The learning occurs in the hidden layers because now data is being transformed using weights, and then a prediction is part of the output, as in this step. Now, if you know what it is that you want to predict, if you say, hey, this is what I want you to predict, and you get the prediction, you're going to start calculating what is called the loss, the mistakes. And usually when you're training a model, there's going to be a lot of mistakes initially. It's going to try to understand what set of weights are the most efficient to be able to predict a closer to the actual value. This loss goes through the process called backpropagation. And backpropagation simply is trying to understand how does each weight contribute to the overall loss. So it goes from the output backwards. It starts calculating, I have these weights, okay? Now, how is this affecting my loss? And it goes all the way back. That's backpropagation. And the idea is that you can actually take weights and you can set them into this graph where you can understand where the weight is from the loss. And if you want to minimize the loss, that means that the weight needs to start going down. And when you start applying these concepts, we use something called as the gradient. And the gradient would allow you to, by default, optimize a value. Since we want to minimize loss, we need to do a negative gradient. That's called gradient descent, for example. So if you see those terminologies, that's pretty much what it is. It's allowing you to minimize the loss, so you can tweak the weights after that, and you will be able to define what set of weights would allow a neural network to perform the way how you want it to perform. So this goes like this: left to right, goes through a process, predicts something, understands where the weight is compared to the loss. It tweaks the weights. It does it again, back propagation, goes down, the weights are moving, hopefully you can see that, and that's the whole process. Like, that's how you are training a neural network. And the input could be, for example, from a log, an IP address, a username, right? So that data, now it's being pushed to the neural network, and the neural network is going to be learning to get to for example, what you wanted to predict or what you wanted to do, right? The output of a neural network is I just learned weights. The weights are known as parameters. And that's what will capture the knowledge, like what set of weights are the right weights to be able to predict something or be able to get closer to what you wanted to do. So when somebody says parameters, we're talking about the set of weights that will show you that the neural network has learned something, and then you can use that in order to perform the task that you wanted to. So this is what I was talking about, feed-forward neural networks. This is just the basics. And in this case, the idea here is that data flows from input to output. Once again, there is not feedback loops. Don't confuse that with backpropagation, right? So in this case, this is very interesting because when you start thinking about how do I apply this to text, to language, for example, to sentences, it's very interesting because with this basic input to output, we don't have a sense of a sequence. Most of the inputs are just thrown through a neural network and make it learn something. But if you want to start processing, for example, as a sentence, sequence of text, you have to do something different. So the first approach was, why don't we just take one input, send it to the neural network, make it do something, send the second one, the third one, and the fourth. So you can start processing input in a sequence, not just everything at once. The problem with this was that some of the output that it is processed at the end might depend on the input that happened earlier. So in this case, this is the concept that people started just innovating. Why don't we just add a relationship between these neural network iterations, and we add the concept of an state. So if I perform some type of computation in one input, I can save that, pass it to the next iteration, and do the same thing all over, right? If the input has 5 words, so how can you process, for example, 5 words or one sentence? That was the concept of what is known as a recurrent neural network. So we're adding recurrence to a basic feed-forward, right, neural network. So this is the foundations, the basics of, for example, sequence modeling, where you could say many to one. What does that mean? Many to one could be, for example, a phishing email. So there is a lot of text, sequence of words, and all you want is to say, is this phishing or not? That's your output. So many to one. All the way to many, which is text translation. And the concept of recurrent neural networks was the basis for that, right? And that's what we're going to focus on, because here's where we start getting closer to language models. And the initial, these transformers, for example, was actually created for text translation. So they were trying to improve the process to do this basic, for example, from English to Spanish and etc., right? Now, this model has the concept of an encoder and a decoder. And this was actually shared in 2014, where you have an input, you have a numerical representation of the input, using the decoder to then decode the input, right? Sounds basic, right? But that's the foundations of translating text. But now, how do you share text with these neural networks? And these are very useful concepts, because everything that you're going to be doing from now on with any model that you see online, somebody doing a blog post, you need to go through some of these initial steps, like tokenization. What does that mean? You have a word, pass it through a tokenizer, and then you have tokens. So in this case, just to keep it simple, one token is one word. Some tokens actually say it's only 4 characters per token. So now the text is going to be split in a specific way. There is a concept of word embeddings. Now that you have your tokens, there is going to be some vocabulary, text embeddings would allow you to then take your tokens. You will be able to see the numerical representations of those tokens. And at the end, that numerical representation of the text is what you pass to a neural network. Now, this sounds very basic, but the concept of word embeddings is that it's not just a text to a numerical value and then let's just pass it to a neural network. There is actually some semantic representation of this text. The relationships between text is actually captured in this embedding. So the words that are similar are going to be close to each other, the numerical representations. And this is super important for language translation in general, any type of natural language task, for example. So if you want to train a language model, you need to understand, tokenize, not just train it, but also even use it. Understand how do you pass your text, tokenize it. Word embeddings is one of your first steps, and then you can pass it to a model. So how does that work from an encoder-decoder using an RNN, right? A recurrent neural network. Basics is you take one word, embed the word, pass it, capture the state, second word, embed it, second state all the way until the last layer contains the embedding of the sentence, okay? And then that's what is used later. If once the model is actually trained, you can actually start translating text, right? Now, this is not efficient because first, large sentences, if you try to pass, of course, one word at a time, it's not gonna be efficient. 2, larger text, the embedding is going to be crazy, the last embedding first, and it's gonna be hard to actually capture this in memory as well. And then at the same time, it does not truly understand the context of words because it's not understanding the relationships in the one word that was in the first paragraph, last word on the last paragraph. It's going to be hard to capture that relationship. So this is why transformers were introduced in 2017, a way to reduce how we send input to this neural network. We come up with whoever did this came up with the concept of positional encoding and also the concept of attention. So when somebody talks to you about transformers, is not recurrence, positional encoding, and attention. And what you see over there on the right, very complex. It's simply an encoder and a decoder. And I say simply, but there is a lot into this piece that something that I would suggest to read a lot of these papers because there is a lot going on in here. But at least some of the words, I hope that they start to make sense. Input of the embeddings. We have also feed-forward neural networks. So you kind start getting the idea there, right? So the concept in here is that in comparison with recurrence, the transformers take all these words at once, captures the embeddings, and then passes it to a neural network. So that's pretty much the initial idea of no recurrence, right? The way how this works is also that if you do not have recurrence, that means that you're now passing one thing at a time, you're losing the order of the words. That's something why recurrence was important. You pass a word, you say, all right, this was first word, second word, third word. Well, transformers take the concept of let's get the embeddings of each word, let's add the position of each word, and that would be position-aware encodings. That's pretty much what it is. So they were able to say, let's remove the recurrence, but it's still, let's try to capture the position of each word and then create the embedding of that word. Attention was also super important. And in here is trying to understand the relationships between words in a sentence. So in this case, the animal didn't cross the street because it was too tired. The word it is actually now referenced to say this word is related to the animal. Like you can see the colors are actually darker on the animal. That was the idea of attention. And as you can see also the words are kind of split. The animal didn't. That's because there was these words are also tokenized. This is another example where you pass a word, the one that we just said, but then what if you change the word a little bit? The animal didn't cross the street because it was too wide. Where does it, where is this connected to? Well, that's connected to the street and not the animal anymore. That was the concept that was introduced with transformers, to be able to understand the meaning of the words relationships in a sentence, in a large text. Transformers now are becoming the cross-model neural network architecture for a lot of things, for text, which was initially for translation, images, and other stuff. You can see that this architecture is what is revolutionizing the world pretty much for the past decade, I would say. So you can actually use a transformer, once again, to train a large language model. And in this case, at the end, the parameters of this model will represent the understanding of the language, right? So keep that in mind. A large language model pretty much has knowledge about language so that you can then start even interacting with this. And if it was trained about specific topics, it will be able to generate text about that topic, okay? And parameters, keep that in mind. You will see that a lot. This model has 100 billion, or no, 100, let's say 100 billion, 100 billion parameters. And you're like, what's a parameter? Well, I hope that now you know, right? That's what represents the understanding, the weights, how they were tweaked through the process of training. And this is what I mean, transformer-based large language models are a thing. And the interesting piece in here is that they actually learn on their own. When I talked about neural networks, you saw how I was showing an actual value and how you start comparing that with the prediction as you train. In this case, and that's because you know what it is that you want to predict. But in this case, we're just sending so much data that there is no way to label every single text, every single sentence in this large data set. So the concept in here is that the LLM captures this input, and then it starts actually masking a couple of words so it can train itself, and it starts predicting what that word was. That's pretty much the basic concept of self-supervised learning for large language models. Now, one concept that is very important is transfer learning, and because words such as pre-training and fine-tuning is going to be thrown everywhere. So the concept here is that you take this transformer, this model, you actually pass large amounts of data with a lot of computation, a lot of money, a lot of days of training. That will give you a pre-trained language model. It's just a model that has a lot of foundational knowledge about the language. Now you can use that for other things. So you can take a pre-trained language model, and then with a smaller, I would say, data set, label, for example, you can provide specialized data. So let's say you want to talk about, let's say, I don't know, fishing. So you will use, for example, some specialized fishing data set, smaller, and then take this foundation model and then be able to adapt it to a task. There are two types of LLMs. The basic is that allows you it can predict the next word. So you could actually provide the things in red, and then it will try to predict and complete your sentence. But when you start asking it questions, it doesn't know what to do. It's like, wait, do I come up with similar questions, or what do you want me to do? There is where the instruction tune models came in, where the initial model was fine-tuned on instructions so that it understands how to actually respond and continue this type of conversations. So that's the in my opinion, how amazing it is that it can actually learn some new ways to interact with you, right? So now, what's a GPT model, right? A GPT model is a generative, pre-trained transformer model. So I hope that you do understand what this means now, right? If I just start my presentation with that, I already failed, because it's really hard to talk about those things in one slide. And the idea here is the same thing. It's a large language model, transformer-based, learned through a lot of data. GPT 3.5 model families actually has 175 billion parameters. So now you know what a parameter is, right? So now it kind of makes sense. It has 96 hidden layers. We know what hidden layers are now, right? And it's trained on 500 billion words, for example. So you can see how this model now has so much knowledge about our language in general and in different topics, right? Just to give you an idea, if you, over time, you can see that BERT GPT-2, 1.5 billion parameters, and you start getting to the 2020, 175 billion parameters. That's crazy. So, and you can see that that was actually in 2020, but we started hearing about this more and more in 2022, and that's because, once again, it was exposed to everybody to start interacting with it, right? And the application that was exposed to the world was actually a pre-trained model that was added some instructions, and now we can keep a conversation with you, right? This is when you start interacting with GPT models, you're going to start getting information now into, for example, the max tokens that you can pass to a model, because there needs to be some type of limitation of how much you can actually ask. You don't want to throw it a large database to the input of the model. Once it's trained, there is some limits. So GPT-3 has all those limits, and those are the names of the models. GPT 3.5 has all those names as well. And now you understand what the tokens are. So now you can see how the tokens change also from GPT-3 to GPT 3.5, for example. So something to keep in mind. And also when it was actually, when the training data also stopped. So it knows things up to 2021, for example, right? And we're going to talk about that in a little bit too. So as I mentioned before, GPT is a foundation model. Once again, it can be adapted to several things now that it has a lot of understanding of language. And those are some of the tasks, for example, that you can start doing with these models. And if that doesn't make sense, we're going to just make it simple in here. So let's take my baby girl, Stevie, and just pass it through Midjourney. That's the prompt, by the way, that created Stevie. Stevie is a foundation model because it understands the basics. It can be actually used for general tasks, like sit, down, come, etc. But if you want Stevie to be specialized on something, if you want her to be a police dog, you need to have a special training for this foundation model. So the same thing, you get an LLM, if you want it to be something very specialized in something, you will fine-tune that model and be able to do something for you, right? Now, one thing that is very important is that if you wanted to do something, you don't just fine-tune this thing and go through the whole process of doing that. There is actually the concept of prompting. What that means is that you can actually adjust the foundation model through some prompts to some queries, and you can make it do things for you. Right? And that's transforming the way how actually in machine learning is happening, right? Now you just have a model, you send a prompt, and it could actually predict things for you, right? This is how you start actually categorizing what it is that you can do with these models. So if you say, hey, I want to use generative AI, GPT models, first question is, what are you trying to do? Well, sentiment analysis. Okay. So what are you trying to do? Well, I have this phishing email. I wanted to see if it's malicious or not. I got this piece of code, and I want to know if the combination of these, for example, Windows 32 APIs, are actually malware or not, for example. So you can start doing things like that. Text summarization. I have all these incidents. I want to start actually summarizing all this and be able to share it with my SOC analyst, right? Stuff like that. So this is how you start thinking about where my use cases will fit, and then you can start Googling or searching, Binging, what it is that you can do with these models, right? So let's just jump to the demos directly. And this is the GitHub repo that I created to share my experiments with everybody in the world. And you're going to need an OpenAI account and an API key. And for those that are wondering, wait, but this is actually expensive? Like, how much money do I put into this? Because as we know, using these models through OpenAI with the API key, it costs, right, to interact with these APIs. But before that, before I talk about that a little bit, some of the modules that I use to do my experiments, for example. And this is some of my usage. I want to share this because people asked me last time I talked about this, like, hey, how much are you spending on this? And in April, I spent 52 cents. And May, for this talk, after doing some experiments, it has been only 17 cents. So for experiments, it's great because, in my opinion, with $1, you can do a lot of stuff, right? So you can use offline models that do not require actually this paywall, right? But you will see the performance is different, right? Some of those models that are coming out are great, but you will see the difference when you start interacting with something like GPT 3.5 with another model that it's open and all that. But that gap might close in the future. So let's start with the basics. Sentiment analysis, and I'm just going to exit out of this. And if you go to the repo, actually, this repo, right? If you scroll down, there is a site that you can just go, and that's the site. This site is a Jupyter book. So I also have the code in the repo, so you can pretty much take your notebooks, your markdown files, and expose them in a site like this as a wiki, and then the notebooks can actually be executed from the site as well. So let's start with the sentiment classifier. And I'm going to make this bigger. So 1 second. So that, and is that good for the back? Yeah? Okay, we're good. I don't know how you do it. I can't see that far from there. But in this case, what we're doing is just importing OpenAI libraries. We're setting our variable OpenAI API key. That's the basics. And then, you know what? I think I can actually make it probably a little bigger. There you go. There you go. All right. So then we create a basic function. Then what we're doing in here is we're picking a model, GPT 3.5 Turbo. And then we're actually creating this OpenAI chat completion. This is going to hit the chat completion API of OpenAI. We're setting the temperature to 0, which means I don't want you to give me a lot of, don't be creative, just answer the question for me. If you want it to be more creative, then you change this to 0 to 7, for example, right? So just something to keep in mind that I didn't know until I started reading some documentations. And this basic function right here would allow us to then pass a prompt. And when you create a prompt, you have to be very specific. For example, in this case, I'm saying, hey, I'm going to do this, but I want you to focus on the words that are between these two sets of strings, right? And so what we're doing here, so in this case, account email verification code, enter now and reply. I wanted to see if it can actually think that this is phishing as a subject of an email. And I just run the prompt, and then it says, it's benign. This email subject text appears to be a legitimate request for. So it just took knowledge that it knew from the web on its own when it was trained, and it just said, that just doesn't look like phishing to me. Right? So that's just a basic example of sentiment analysis, but how can you actually make it say, hey, that actually could be a phishing email subject, right? Here's when we start actually doing the concept of few-shot learning, where in the prompt, you provide a couple of examples as well. And that's how the model is adapting. It's saying, wait a minute, okay, so I have some of this, you label it as malicious, another malicious, and this is benign, for example. This is just an example, once again, experiment. This at a scale is going to be different, but just to show you how this model adapts. So once it goes through all of this, then I pass the same subject, and it says, oh, wait a minute, yeah, that's malicious. Based on how you were telling me that some examples, I could say that's malicious. So that's how you mix few-shot learning with some of the basics of prompting using a model, for example, in GPT, right? From the GPT model family. The other example is going to be text summarization. What does it mean? We do the same thing. We import the libraries. We set our API key, right? We create our function to do completion, and now we use that for something else. So I took a differ report, some of the command lines that were shown in a report, and if I share this with a junior analyst, they will be like, I don't know what's going on. I mean, I can probably read, I can spend some time, maybe do it in my own environment and figure out what's going on. So you can pass this, and you can actually say, your task is to understand a few commands executed by a threat actor and then generate a summary of it and summarize the review below, right? And I just pass the evidence, the evidence on the top. I do that, and at the end it says, well, the threat actor is disabling Windows Defender, is deleting files. So it starts explaining exactly, summarizing all this knowledge. And here's when you start getting, in my opinion, junior analysts, or not only junior analysts, but any analyst, right, in general. Sometimes you will not be that familiar with the language that is being used by a threat actor, let's say. So you might want to summarize some of that, right? So that's one example of how you can summarize information that might not be that clear for you to understand. Next example is going to be attack GPT. And before we do that, we're going to go to this slide right here. And hopefully that makes sense. Let's see. Yeah. So as we mentioned before, the data that this was trained with was up to 2021. So even right now, if I ask about a MITRE attack technique that came in the last release, it will not know about, for example, right? Because up to 2021. Another thing is internal knowledge, like companies are creating their own knowledge. For example, threat intelligence, right? How can I make it actually summarize or answer questions about my own knowledge? So this is one of the examples that we're going to see in here. And I was trying to find a way to show a public experiment about Intel. If you think about MITRE attack, they have attack groups, and every single attack group has adversary tradecraft or tactics, techniques, etc., mapped to every single group. That is what companies do internally. They have documentation of a specific threat actors, and they map all these tradecraft to the threat actor. So how can I query all this knowledge and ask questions that might take me a while to figure it out? So in this case, what I did is I took a Python library that I built. It's called AttackCTI. It's going to connect to the taxi server of MITRE attack that has attack information in the sticks format. I'm going to create local documents of that knowledge. I will tokenize all that information. So now we know what, right, tokenize is. We're going to embed all these tokens. We all know, right? And then we're going to push it to a vector database. A vector is the numerical representation, like that embedding. So vector databases, it's a thing already, and it's growing, like the whole usage. So in this case, everything's going to be there. So now when I ask a question to my LLM, it's going to first embed my query. It's going to do a similarity search. So it's going to say, you have this question. How similar is this question to the knowledge that I have? Once it retrieves documents that are relevant to your question, then it passes that context to the LLM and with the question. So it can answer questions about your knowledge. Of course, this is an experiment, and this is going to go to OpenAI, right? Because you're hitting APIs. So this is just for experiments. Don't use it. Like, send all your private information. And of course, there are options enterprise-wise to do this, of course. Oh yeah, and before doing that, so we're going to jump directly here. So this is the notebook. And this is going to do what I told you it's going to do, right? So the explanation in a graph is better than going through every single slide and maybe doing it where you're just looking at code. In this case, we initialize the client. I'm just going to go slowly here. We're going to create the group's knowledge, connect the database, right? This is one example of one group in attack. Create the documents. I want to scroll down. This is where I define how I want the document to look like, for example. And I'm just going to scroll down. All of those are markdown files. If you go actually to the repo and you go to experiments and you go to attack GPT, and then you go to knowledge, if I'm not mistaken. Yeah, you're going to see all these files in here. So the files kind of look like this. Name of the actor, description, etc. And all the information, tradecraft mapped to the threat actor, right? So that's pretty much what it does in here. So this group is going to do that. So I'm going to scroll down. And now we generate the embeddings. So in here, I'm using tick token in order to calculate the tokens per document. And that's what I do in here. I actually go through every single document. I'm going to scroll all the way down here. And of course, the notebook is already public, so you can go and see the specifics. And in here, it tells me that there is some documents have 176 tokens minimum. Some of them have 7,350. Some of the limitations of these models is the number of tokens that you can pass. And if I'm not mistaken, GPT 3.5, it's like 4,000 something tokens per question, let's say, right? So we have to split these documents. That's the process of data, let's say, cleaning and normalization in here. So we're going to split the document. And then at the end, it's going to, let me just make sure that I was able to have 534 chunks. So I split all my documents. And what does that even mean? If I go to this GitHub repo again, and I go to the database, I actually created this JSON-L file. And in this file, you can see, hopefully, I'm going to make this bigger so that way you guys can see it maybe. Yep, there you go. So as you can see, there is 2 lines right here that do have the same ID with a 0 and a 1. That means that this document was split in two chunks, okay? So that's what the splitting is. And if we go back to the code, something that I did also was, if I just go back to the code real quick, 1 second. In here, oh, I don't have the, sorry. All right, so in one part of this document, I actually, here it is, chunk size. I was able to define what is the size of each chunk that I want to do, and then also overlap. What does that mean? When you have large documents, the name of the threat actor might be on the top, but then you want to chunk the last piece and might not have a relationship between the threat actor and the last piece. One technique is to say, let's get a chunk, and then the next chunk, let's use 50 tokens that were the last tokens of the first chunk. So that way we can keep a relationship between each chunk. Or you can just append the name of the threat actor in every single chunk that belongs to the threat actor, and that's how you keep the relationship between the knowledge and the threat actor, right? And then at the end, I actually exported this as JSON, and now it's also part of the Hugging Face data sets. This is my first contribution to Hugging Face. This is a way, I still contribute data sets to the community, cybersecurity, but now why don't we take all this knowledge, how I chunk the documents, and now make it available so people can also import it directly in their notebooks if they wanted to with the Hugging Face modules. And then at the end, we create a database. So in here, I'm pretty much first saving everything to a pickle file so that way I don't have to do this whole process again. Because when I use embeddings, I'm actually using OpenAI embeddings in here. So I'm doing this call so I can save all these embeddings and just have it available. Once I have my database, now I can ask questions. I set up my OpenAI key. I set up my database as a database that I can retrieve knowledge from, and then I get relevant documents. What are some phishing techniques used by threat actors? It's going to go through all the knowledge. It's going to give me relevant documents, and then I can pass my question to the LLM, and now it's going to summarize, oh, threat actors have used spear phishing emails with malicious attachments, links to HTML. It's how you actually would query all your information. Currently, you use, let's say, either SQL, Graph, and you have to learn how to do the Cypher queries, SQL, all this stuff, or even specific language, right, to query knowledge. So this is a way how you can do it. 2 examples, hopefully we have time in here, but it's gonna be Bloodhound GPT. So this is a code generation example. So now we can actually tell the LLM to create cipher queries based on natural language. So if I write a sentence, I wanted to translate that to cipher, and then pass that to Bloodhound, for example. So this notebook walks through the process of deploying a Neo4j Docker image, using the also the once again LangChain modules to be able to connect to this database and be ready to start writing cipher once you ask questions. I use the Bloodhound DB creator Pythons in this notebook to do all this. I actually have this script that actually works in the GitHub repo. And then you generate new data as an example, right? And now the model is going to learn the schema of Bloodhound. So now it knows that I know how to do cipher because I learned back up to 2021, I know how cipher works, so I can generate cipher, but I don't know your schema, so give it to me. This is what it does, right? And then we can say, we can do a test. We can just look for users that have a service principal set. First, you do cipher, so you can just validate that there is an output. And then you can use the similar concept that we did before, and then you say, what users have a service principal name set? And then you can see the LLM producing the cipher for you. You don't have to do that, and then it responds that to you, just as if it was talking. You can also do other cipher queries, and you can see how you can actually see the LLM doing it. But in this case also, in this notebook, I show you how you can see that the LLM in some of these queries is actually not giving you the right answer. It's because I'm not being that specific. And that's where our jobs is to improve this process, and that's what we're still needed, right, to understand how to interact with this stuff. So this notebook walks through this whole thing. It's super cool, but they cannot do a lot of complex stuff, and that's something that it's known. And I don't have much time, but I'll just do this. I had one that was actually, oh, there's a fly. I had one that was for the last one, just to finish this, row tools. So row tools, right? This just happened right now as Direction was actually talking. I can actually use also my LLM to start interacting with the row tools, SQL database, and it understands SQL. So now it can connect, learn about my tables, and I just pass a question, and it will actually respond to me. And that was super cool to be able to use some of this to automate this process. So you can enable this in your own knowledge, and there is a lot that we can do. And the future is agents. Actually, the last example of row tools, you will see that there are actually the LLM itself. It's saying, let's run this query. It doesn't work. Let me do it again. Let me learn something different. So it's going to learn the process as an agent to produce the right knowledge. Thank you very much. I hope that this was useful, and these are some of the links, and you can follow me on Twitter. Feel free to do that.